Okay. Okay, so thank you for that, and thank you all for coming. So we're ready to start. First off, we have the Theodore from Forum, who's going to tell us about the very great days of the video. Please, take care. I'll give you a 5-minute warning.
So this thing somehow scrolls in slides.
Can you maybe click to
Okay.
so that
So thanks everyone for coming to my talk. I'm going to be talking about the covariant base formalism in the language of all-infinity algebras. This is work in collaboration with my student Vinicius, who's somewhere here. He's right there, and also Adikin Pirat, who's now at UC Davis, a postdoc at UC Davis. And okay. So the goal of what we're trying to do is we're trying to find a Hamiltonian description of string theory. So what things one might like to do with that, for example, are compute charges of D branes, or have some kind of intrinsically string theory notion of gravitational mass, or possibly applications to tachyon condensation and black hole entropy. So it's just a tool that one can use to perhaps address these questions. So to derive the Hamiltonian formalism, one always starts with the Lagrangian, almost always starts with the Lagrangian. So then the question is, okay, so what is the Lagrangian of string theory? And then the answer is what's called string field theory. So string field theory is a field theory of fluctuations of a background in string theory. So there are basically two types of string field theories. You have an open string background, that's a background that's representing some configuration of D branes in some background space-time. Then the fluctuations of these D branes is governed by open string field. And if you are talking about a closed string background, that's basically space-time in itself, then the fluctuations of the closed string background are described by closed string. So string field theory is naturally what you might call a BV field theory. And so what is a BV field theory? So it's covered by an action which is a priori given as an expansion in powers of a field theory. So you have the quadratic term, a cubic interaction, and quartic, and so on, many different types of interactions. And there are various objects here which are written. And these objects are defined in such ways to ensure that this action automatically satisfies the Baddelin-Minkowski master equation. So, okay, so that's what BV field theory is. So let's talk a little bit more about what the ingredients are. So phi is the dynamical field of the theory, and it's an element of some graded vector space. Okay. And this graded vector space comes with an inner product, which is actually an odd symplectic structure, which is written with this lowercase omega. So this odd symplectic structure is the thing that defines the BV antiproduct. And in addition, the theory comes with a sequence of higher products. Right here is Ln. So these are maps which take n fields and spit out fields. So they multiply n fields and give you another field. And so you have, in principle, infinite sequence of these higher products, starting with Q, and then L2 and L3, and so on. And the point is that this vector space, together with this inner product and these higher products Ln, define the structure of a cyclic all-infinity algebra. Okay. So these are the ingredients of a BV field theory. So in string field theory, this vector space H is the space of states of a two-dimensional conformal field theory, which is describing the world sheet in the background that we're interested in fluctuations of a specific background of string theory Then there's the strings moving in that background. There's C of t, the state space of that C of t is this H string field theory. And this this omega and these ln's are defined by certain correlation functions in this two dimension. Okay, but it's important to emphasize that this L infinity algebra structure that I just described can actually be realized in any field theory if you know how to define your vector space H and this and omega and Ln in the correct way. And this basically follows as a consequence of the universality of the BE formulas. So, so what this means is that our approach to Hamiltonian mechanics that I'm about to describe is actually completely general for any field. So this work was motivated by initially by questions concerning the decay of unstable d-branes in string theory. So in the language of string field theory, the decay of a d-brane is represented by some time-dependent classical solution of open string field theory. And this is a time-dependent string field, is a complicated object, but you can kind of conceptualize this, what this solution is doing in terms of what the tachyon field is doing. Okay, and you can visualize, okay, in the decay of the d-brane, this tachyon field is moving as some function of time. Okay, and you can imagine it as moving inside some effective potential for the tachyon field. Okay. So this effective potential has an unstable maximum, which represents the original unstable d-brane configuration, and it has a minimum, which represents no d-brane. Okay. So a decay process represents this tachyon field kind of moving around in this potential. And one can consider a type of solution where the tachyon field kind of rolls off the potential towards the unstable vacuum and then stops just short and then turns around. So gradually going up and turning around, going back. So this is a particular type of time-dependent solution representing the decay of the d-brane. And this turnaround point is given by some parameter lambda, which tells you something about the solution. And a question that one can ask is, what is the energy of this time-dependent solution as a function of this turnaround point, this expectation value where the tachyon field rolls up, stops, and then turns around? Okay. So this was computed a couple of years ago by Cho, Mazel, and Yin in a kind of interesting way. What they did is they kind of used a formula for the symplectic structure on the phase space of string field theory that was proposed many, many years ago by Edward Witten. And they evaluated this symplectic structure on the solution and manipulated it into the form so that into the form of delta t times delta e. And then by figuring out what this delta e was as a function of this turnaround parameter lambda, they were able to determine the energy of this solution as a function of lambda, this time-dependent decay process. So, but there was a problem with their calculation, which is that Witten's actual proposal for the symplectic structure was not really well thought, essentially. Okay. So, but they still managed to get a sensible answer by throwing away the infinities in the right way. Okay. They justified their prescriptions to themselves, but ideally one would like to know what the symplectic structure is on phase space in string field theory and compute, and this should be a well-defined object, and one should be able to compute it and get the right answer. And normally one can derive the symplectic structure on phase space directly by starting from the classical action. And the question is, why don't we do this in string? And the answer is because string field theory is non-local. Okay, so the Lagrangian depends on an infinite number of time derivatives of the string field. Okay. So in principle, then one can try to attack this by thinking of it as some kind of n derivative Lagrangian with n very large. And then there is a well-defined prescription for deriving the symplectic structure on the phase space of the Lagrangian that was given by Ostrogrovsky in the 19th century. And what you do is you just, you have for an n derivative, capital N derivative Lagrangian, you have n coordinates, capital N coordinates, and capital N momenta given by these formulae. Okay, the coordinates are given by some derivatives of the position variable, and then this complicated combination of derivatives of the Lagrangian. And then once you derive the coordinates and momenta, then the symplectic structure is just given by having a delta, actually it should be delta p, delta q, sorry. By delta p, delta q, 1, 2, 3, and up to capital N, and that's your symplectic structure. So then one can think, oh, okay, maybe we can do this in string field theory by taking some n goes to infinity. So unfortunately, this doesn't work, okay? One way of seeing it is that already if you specify half the phase space variables in the infinite derivative limit, you're already saying that an arbitrary Q of t can be a solution. Okay? Because you specify all derivatives of your variable at time equals 0. So half your phase space variables already completely determines the solution. And you can actually look in a concrete non-local model. So one useful model to think about is p-adic string theory. So this is a kind of a toy model of string theory, but important thing for us is that it's given by some scalar field that's governed by some non-local action of this form, and you can look at the free equations of motion of this action, so we can make focus on the action form, and that's just given by p to the box on phi equals 0. So this is an infinite derivative free equation of motion, but it actually has no solutions. Or no solutions besides phi equals 0. The reason is because you can basically divide by p to the box. So this equation has no solutions, and you certainly cannot specify an arbitrary phi as a solution of this equation. So it's just not true that that there's something sensible that you can get out of taking the infinite derivative limit of a higher derivative object. So how do we think about this? So, okay, the purpose of the canonical formalism is to construct phase space by providing an explicit parameterization of the space of initial value data. Okay, so that's what this Qn and Pn are that I looked at in the previous slide. They represent some coordinates on the space of initial value data. But if you have a non-local theory, it's not clear that solutions can be generated from initial value. So, this motivates the introduction of the covariant phase space formalism. So the covariant phase space formalism, okay, various motivations for it, but basically all that we're saying here is that we don't want to conceptualize phase space as the space of initial value data on some Gaussian surfaces. We wanted to go directly to the heart of what phase space actually is, which is it's the space of classical solutions, so it's space of solutions to your field equations equated up to gauge solution. So the point is that a non-local theory may have solutions, the field equations may have solutions, even if they're not parameterized by initial value data. So any questions? What am I doing on time? Okay, so now let's get into more technical things. So how do we talk about covariant phase space at the level of a EV action, the kind that inhabits field theory? Well, we have the space of fields phi, which, as I said, is some linear vector space H. And inside this vector space, there's a surface which represents solutions to the classical equations of motion. Okay. So classical equations of motion look like this. So you basically have some kinetic operator on the field and then a bunch of interactions, and this sum should add to zero. So if you have a field phi, which satisfies these equations of motion in the PV field theory, then this phi is said to be in what's called the pre-phase space. So it's the pre-phase space is just space of classical solutions. And then one can think about this space as a manifold, and one can define a complex of differential forms on this manifold. And the exterior derivative of this complex we're going to write as delta. So this is not a variation. This is an exterior derivative, be like an object. By taking the exterior derivative of the equations of motion, one finds that the differential delta phi has to satisfy this equation. Okay? Where this q phi, some operator, which you get from taking the derivative of that equation, which represents, it's the kinetic operator for fluctuations around this classical solution phi. Okay, so the differential satisfies this constraint. The pre-phase space in general will also be foliated by gauge orbits. Okay, so there will be classical solutions which are gauge equivalent, and these gauge orbits are generated by vector fields, which denote as lambda, which generate the gauge transformations. And so the infinitesimal gauge transformation, so the derivative of the field of phi along this vector field is given by this equation, q phi of length. Okay, so that's the form of the infinitesimal gauge transformation in the PV field. Okay, so the pre-phase space is the space of solutions, and the phase space is the space of solutions modulo these gauge motion along these gauge lines. Okay, so we know that phase space should have symplectic structure. Okay, so we can have a two form on pre-phase space. We can have a two form on a space of classical solutions, and this two form will also be a symplectic form on phase space if five conditions are okay. Okay. The first is that this two form has to be closed with respect to this exterior derivative. The second is that zero tangents vanish, as I say. So if you contract the symplectic form with the vector field of a gauge transformation, you should get zero. And that's because on phase space, the vector field of a gauge transformation is actually the zero vector. So that just says that zero vector fields actually vanish. Okay. The next condition is that the symplectic form should be gauge invariant, which should be invariant under flows generated by these gauge. These vector by this gauge transformation vector field. And then there's also non-degeneracy, which in this context means that if you have a vector field which vanishes when contracted with this two form, that vector field must be the vector field which generates a gauge transformation. And the final condition is that the two forms should be conserved, which means it should be independent of the choice of class size. Questions on this? So these are conditions.
The last one is the least obvious to me, that it has to hold. I mean, I agree it's a nice property that you may want to have, but there might be physical systems where you can't achieve conservation. So
Yeah, so you can always, so I will now explain what this actually means. So I put this in quotes because it's not clear. Where does the time slice fit in this picture, right? This picture of this action and these equations motion, and there's no coordinates, no field. So what do we mean by independent of the time slice? So this final condition is, as you say, it's a little obscure.
I have a question. So what is the exact difference between non-regionality and simultaneity in Spanish?
Well,
application direction.
Well, yeah, so non-degeneracy means that that if you have a vector field that's in the kernel of the symplectic form, that vector field has to be zero. That's what it's saying. So this is just saying that vector fields which are zero are in fact zero. It's like, you know, okay. Yeah, so now we're getting to this question: what is the meaning of a time slice having non-local field theory? So the way we conceptualize what a time slice is inspired by an idea of Witten, and it's okay. The idea is to introduce this operator on a vector space H, okay, which we call the sigmoid operator. And so it just takes H into H, and it satisfies some boundary conditions function of time. Okay, in the infinite past, the sigmoid operator should be zero, and in the infinite future, it should be the identity operator. So when we introduce this operator, we're implicitly assuming, or we have in mind, that we have a field theory which has some notion of time. And there's some infinite past and an infinite future. Okay. So we're kind of putting that in the definition of this sigmoid operator and its boundary conditions. So the idea is that, okay, so this sigmoid operator starts at zero and then goes to one, okay? And in between it does something funny or abstract. It changes in some way as it goes from one configuration to the other. And this fluctuation or this change is actually supposed to be a generalized notion of time slice, which can be meaningful also in a non-local field.
Does it have to be monotonous, or it could oscillate?
Yeah, it could oscillate, or it could be even something, you know, something more abstract. It's a completely, in principle, a completely general operator on this vector space of fields.
So does it have to be bounded between 0 and 1 bit?
No. So this is just a shoot. It's just somehow. Okay, just okay, it makes between the different fields, you know, depends on the things in principle. Usually it's not useful to be too general, but
yeah. Will the non-monicity be important for applications? And is it important that it's not necessarily monotonic?
It's not important. Yeah, so whether it's monotonic. So when you're talking about monotonic, you're thinking about some function. So that would be a realization of this sigmoid, where it acts on this vector space through multiplication by a function of time. So in general, the sigmoid could be something.
Oh, it's a space.
The only thing that you really know for sure is that it starts at 0 in the beginning and ends at 1 in the end. So this is how we introduce the notion of time slice. Okay? And with this, there's a formula for the symplectic form that we propose, which is this. And you can show that with this formula, all 5 conditions are okay. And so, okay, the formula is given in terms, it's a 2 form, it's given in terms of differential of 5. Okay. And this inner product and commutator of the sigmoid, and this Q5, which is the operator describing fluctuations around the solution form. So the first point we want to want to make is that these consistency conditions follow from very general properties of L-infinity algebras. Okay, and therefore this formula is not just a formula that applies to string field theory, but any field theory which has been expressed in this DG language. Okay. The second point is that both 0 and 1 commute with this operator Q file. Okay. And for that reason, this operator, this commutator operator, is localized to regions in time where this sigmoid is changing. Okay. And this localization of the symplectic structure is how the time slice is realized. Okay. The third point is that this formula almost vanishes because this differential delta phi satisfies the linearized equations of motion around the solution. That is, remember that delta phi, the differential, is killed by Q phi. Okay. So the reason why this doesn't vanish is because this operator Q phi would normally satisfy some version of integration by parts. So this condition is called cyclicity. Okay. It's normally satisfies cyclicity condition, but because the fields and the sigmoid don't vanish at past or future infinity, this condition is breaks down because they are boundary terms. Okay, so that means that this formula is not actually 0, even though Q phi annihilates delta phi. Okay. The fourth point is that related to the previous point is that you can easily see from this that the symplectic structure is conserved. And the way you see it is you consider an arbitrary variation of the sigmoid, okay, which an arbitrary variation has to respect the boundary conditions both in the infinite past and the infinite future. So the variation of the sigmoid will vanish strictly vanish in the infinite past and future. And because of this, there can be no boundary terms when you integrate by parts. And that means that Q phi can act on both of the delta phi's to give exactly 0. And that's how you see that this thing is actually independent of the choice of the sigmoid, which is saying the same that's independent of the choice of time slice. Okay.
Was there some condition of non-degeneracy on omega? It's gauge directions invertible.
Yeah, non-degeneracy was one of these 5 conditions that the interaction with the vector field implied that the vector field is gauge transformation. So actually, to prove this, we don't prove this in our paper because proof requires a Poisson bracket, which I won't want to select.
But does it put some conditions on what sigma could be? If, for example, if I take sigma just to be some function of time, then it's going to commute with Q, I guess.
Yeah, so it does. Yes. If you look at it in details, there will be some conditions based on the growth of your solutions in time. You will find that sigmoid should vanish quickly enough to make sure that the quantities like symplectic structure and the conserved charges, that these kind of quantities should be convergent when you compute them. So if you have solutions like a rolling tachyon solution that's blowing up exponentially, and you need to make sure that sigmoid is going to 0 fast enough that when you compute the energy, something like that, that when you do that integral over time, blowing up exponential profile won't overwhelm the sigmoid. So there are kind of technical conditions like this that one can look at.
I guess it's naively, if you just take a sigma that would commute with Q, then it would not work.
Yeah, how can you do that? Yeah, so I guess if you could choose a sigmoid that commuted with Q, then your phase space would be zero dimensional. That's what that would mean. I think in practice one, this sigmoid has to go from 0 to 1, so it has to be a function of time. And in order for that function of time to commute with Q, that means it's Q would not have to not be, it would have to be a constant of some operator.
Okay.
That doesn't take any derivatives of the effective time set. But I guess.
Okay, so I didn't realize
that could happen in principle, yes. So now we'll give a few examples. So we'll start with a phi cube theory. So phi cube theory can be written in this dB form if you want to be formal. You can write it. You could find the omega, the q, and the L2 such that the phi cube action looks like this. Okay, and then you can plug into our formula to compute this symplectic form, and you find this. Okay? So now we don't have time slice directly yet. So our symplectic form is integrating over all of space and time. Okay. But here we find, instead of a time slice, we find a sigmoid. And so the derivative of the sigmoid is contracted with 2 delta phi's and a partial unit. So that's what the symplectic form phi cube theory looks like. The first point is because the sigmoid appears differentiated. The symplectic form is localized to regions where the sigmoids. So that's how we kind of get our time slice. And actually, we can reproduce the time slice exactly if we choose the sigmoid to be a step function, which is 1 in future of time equals 0 and 0 in the past. Okay. And then you take this derivative and you find a direct delta function times this Honecker delta, which sets the index equal to the time direction. And then if you plug this into our previous formula, this 4-dimensional integral will collapse to a 3-dimensional integral of the time slice. This partial mu delta phi will turn into the time derivative of delta phi. And you see that this is exactly the form of delta p delta q that you expect for phase. It's the first point. The second point is that the symplectic form is almost 0 because this delta phi satisfies the linearized equations of motion around the solution phi. And so one can turn now in this context try to understand why the symplectic form is not 0. So we start with our formula here. And what we want to do is we want to integrate by parts, taking this partial mu act on here. So we integrate by parts, and in doing that, in principle, we generate a boundary term. Okay, so let's ignore that for a moment, but and focus on what happens when the derivative acts inside here, and we find one term where partial mu acts on both delta phi's, and another term where we get a box. This term is 0 because the square of the on object is 0. And this term, what we do is we use the equations of motion to replace box delta phi with m squared plus 2g. So just by using the linearized equations of motion, you can make this replacement. And now this term also vanishes because it's got 2 delta phi's, and the square of the on object is 0. So we find that indeed the symplectic form is 0, except that we're not accounting for this boundary term. And if you look at this boundary term more carefully, you find that at t equals infinity, this sigma is 1, and at t equals 0, the sigma is 0. So this thing reduces to this boundary term evaluated at t equals infinity, which we see is exactly the delta p delta q that we had in the previous slide. So we see that the boundary term at infinity is in fact this whole symplectic structure itself. Yeah.
So in the previous case, it was evaluated at t equal to 0, not at t equals to infinity, right?
Yeah,
Because you
so
had
in
the
the last
delta.
case, yeah,
Yeah.
so, right, last case was valued at
Yeah.
equals 0, but, yeah, but it's conservative.
Yes.
So, okay, and then the third point is that if we do the same calculation with the sigmoid replaced with a variation of the sigmoid, then there won't be that boundary term. So indeed, we find that the symplectic structure sits in. So another example is returning to this p-adic string theory model, this non-local scalar field theory model. Okay, we can also rewrite this in BV language, and we can even choose our sigmoid to be this step function, which is 1 in the future of t equals 0 and 0 in the past, and try to compute the symplectic structure and see what we get. And we get this formula. Okay. So what can we say about this formula? Okay, so the symplectic structure, just in the case of the p-adic model, it doesn't localize to t equals 0, even if we choose this sharp kind of step function signal. So in this case, because the theory is non-local, we're not able to actually create a sharp time slice for the symplectic structure. Instead of the structure here, okay, we have two integrals with delta phi's and then some Gaussian in their separation. So one can visualize that as if we have somehow we have time equals 0, and in the future, time equals 0, and these delta phi's represent differentials of the momenta, and in the past, they represent differentials of the coordinates. And these objects are somehow conjugate to each other to a degree which is suppressed by a Gaussian of their separation. 5 minutes. Okay, so need to run out of time. So
can you calculate the energy of the rolling actor and the periodic string theory using this?
yes, yeah, it works. So, yeah, so we'll also do that and check that it's working. Okay, also one can use this this symplectic structure to compute the symplectic form in general relativity. And there's an issue concerning boundary terms in the definition of the symplectic structure in relativity, and they maybe it's running out of time. I won't go into detail there, but it turns out that this formula computes the correct symplectic structure for general relativity, including the boundary term, and that was subject recently. So then we can talk about just with some applications to string field theory that we've worked out in the last year. So one thing that we did is we revisited this calculation that shown us out again, using our new symplectic structure, which is now finite. Okay, unlike the original idea, which had these infinities, this new symplectic structure is finite, and in Witten string field theory, if you expand out the Q phi, you can find it in this form. And we showed by computing this that you correctly reproduce the energy of the decaying D-brane background using a symplectic structure. We also looked at solutions for tachyon lumps that have been boosted to some velocity v.
So these calculations you need to certain order in lambda.
Which one?
The rolling tachyon energy.
This one, yeah. So it's the first interesting one.
What will it take to get the exact?
Well, I'm not sure one. Well, what would you like to do? Would you like the exact solution in CVH? So you probably need the exact solution in CVH. Or one could try to do an analytic solution.
Yeah.
And that could be done. I haven't tried to do it, but I would do this exactly. With a solution. Yeah, so, but this was done to the first interesting order. And we also looked at solution, we looked at the tachyon lump and we performed a Lorentz boost so that this tachyon lump is moving at some constant velocity. And then this space of solutions is a two-dimensional phase space, given parameterized by the origin of the position and the velocity. So you have a particle with the position and the velocity, and you can compute the symplectic structure from our formula. And this symplectic, and so the momenta should be given by mv times the Lorentz factor. And this gives you kind of an interesting way of computing the tension of the deep-ring. We show that we correctly reproduce the deep-ring tension. We compute the momentum from the symplectic structure this way. And finally, we also looked at solution for electric field on a deep-ring, which is a time-dependent solution generated by a marginal operator of this form. And you can use the symplectic form to compute the energy of the solution as a function of the electric field on the deep-ring. And we showed that this energy agreed with what you get from the Bornfeld action. Okay, and then finally, so we want to set up Hamiltonian mechanics, and it's not enough just to talk about the symplectic structure. You also want to talk about conserved charges and Poisson bracket and so to speak. So there are also some nice formulas for conserved charges. So here's a formula for the conserved charge that should come out in a paper soon. I'm still trying to figure out how to present this. It's actually quite a beautiful formula, but I'm trying to figure out how to present it in a digestible way. But this is one version, so you have these this inner product of these two objects, and the critical thing is this object here, which is given by some combination of the equations of motion and the operator, which is generating their symmetry transformation.
What is S?
What is this?
S.
S is a auxiliary parameter
Okay.
in that you use to somehow deal with some combinatorics.
So there's no physical meaning you want to attach to this parameter?
No, so in fact, the expression doesn't depend on the field at S. It only depends on the field kind of at the boundary. So this expression is actually a total derivative in S. But you have to, this formula is kind of complicated, but so this way you can like write down Hamiltonian or supersymmetry generators, or, electric charge. You can write down these kind of things. If you know the symmetry of your theory, you can write down, and the equations motion, you can make things. It's kind of Noether's theorem.
And when you say conserved, you mean with respect to variations of this sigmoid?
Yeah, so it's independent of this sigmoid.
Okay.
It's conserved in that sense. And
But you make the field depend on any parameters, and how does this enter the field?
yeah, the thing is kind of a total derivative with respect to S. So the point is that the string field theory action comes with like 1/n factorial, right? The problem is that is dealing with that combinatorial factor. Okay, so what we do is we prefer 1/n minus 1 factorial rather than 1/n factorial in order to get that extra factor of 1/n. We do it by doing the integral of x to the n. So, or x to the n minus 1, so that we get the x to the n over n. So that 1/n, that combinatorics is the reason for this parameter S. And it seems rather stupid and trivial, but somehow when you're able to do that, you're kind of able to write this formula in a way that, okay, I don't know if it's that beautiful. I mean, maybe you have to stare at it, think about it for a little while. But it's a lot more beautiful than if you write everything out in terms of the multi products of, principle. The action has this infinite list of LNs, and the symmetry generator, an infinite list of their products and their going to be composed in some complicated way or some double sum. So if you write everything out in kind of full, like explicit, like string field theory way, this formula looks rather. Okay.
So the actual string field is the value of phi at x equal to 0 or something.
Yeah, s equals 1, actually, s equals 0. It's vanished.
Nice.
Let's see if we can wrap up. Okay. So, you have maybe one quick question, and then we'll be almost the data.
So the expression for the concept charge also probably doesn't depend on the sigma.
All right, so it's conserved in that sense, it's independent of the signal. Um, It satisfies its own list of consistency properties. We want to conserve. There's also the Poisson bracket and stuff like that. Yeah. So these things will come out soon.
So no matter what algebra this charge satisfy, you can always build the node form.
Sorry.
So sometimes concept charges can satisfy their own algebras, right? And
Yeah. So you can show that with the Poisson bracket that there's an algebra being satisfied by these conserved charges, which is of the expected form. And there's also an expression, a kind of nice, very simple expression for the central charge in this as well.
Okay. Let's thank you, Ted, again.